Hi everyone. In this video, we are going to look at an actual gas turbine cycle and how it deviates from an ideal gas turbine cycle. The actual gas turbine cycle is a gas turbine cycle which contains some irreversibilities in some processes. For example, in the compressor, the compression may not be isentropic. Instead of isentropic compression from point 1 to point 2s, it would be an actual compression from point 1 to point 2a. Similar to expansion, instead of expanding isentropically from point 3 to 4s, it would be from point 3 to 4a. The irreversibilities in heat addition and heat rejection processes can also occur in some form of pressure drop. As the working fluid flows through the combustion chamber in process 2A3 or cool down in the atmosphere in process 4A1, you can see that we have different kinds of irreversibilities taking place in various processes in an actual gas turbine cycle. When they occur, they can affect the performance of the gas turbine cycle. Now, let's have a look at a calculation example of an actual gas turbine cycle. Here, we'll continue from the previous example of gas turbine cycle in part 2.4. But in this case, the compressor and the turbine are irreversible with 80% and 85% efficiency for compressor and turbine respectively. We want to determine the thermal efficiency, the back work ratio, and the turbine exit temperature or T4A. You can see that the irreversibilities in this cycle occur in the compression and expansion processes as seen from the shape of the cycle on TS diagram. To solve this problem, let's identify what we have and what we want to determine first. At point 1, this state is well defined since both temperature and pressure are given. At point 2, only pressure is given, but the compressor exit temperature or T2A is not known. Similar to point 1, state 3 is well defined. Both pressure and temperature are known. And lastly, only the pressure at point 4 is given. The isentropic efficiencies of both compressor and turbine are given, and we want to know three parameters as shown here. Now, we have to work backward from what we want to what we have by relating them with some relationships that we have learned. We can use a solution map to clearly formulate our solution procedure and then effectively solve the problems. First, we have to classify our parameters into different groups, which are input data, unknown parameters, heat and work variables, and performance indices. Here, we have 6 input data that we have already known their values. They are T1, P1, P2, T3, P3, and P4. We also know 2 intermediate parameters from previous calculations, which are T2s and T4s. But the actual state 2 and 4 temperatures or T2a and T4a are not known. The heat and work variable at isentropic conditions are also determined previously. the heat and work variable at actual condition, or W12A, W34A, and Q2A3 are not yet calculated. Finally, two performance indicators, which are Brayton cycle and back work ratio at actual condition, are to be determined. Next, we start to establish relevant relationships between variables, starting from the parameters in the outer layer, which are the performance indicators. The Brayton efficiency could be determined from the definition of what we get over what we give, which is the net work output divided by the heat input. Here we have the equation as shown in the first yellow box. The back work ratio can be determined from the definition of work input divided by work output. That would be W12A divided by W34A. We can now move on to the next layer to determine the heat and work variables. The actual compressor work can be determined from the isentropic efficiency definition. To achieve what we want, we need W12S and compressor efficiency. The actual turbine work can be determined from the isentropic efficiency definition. Similar to process 1-2A, we need W34S and turbine efficiency to get W34A. The actual heat input can be determined from the mass and energy balances of process 2A3. We need T2A and T3 to get Q2A3. However, we don't know T2A at this stage. We can see that we have only T2A and T4A left to be determined. We can get T2A and T4A from the mass and energy balances of process 1-2A and process 3-4A respectively. We have now completely formulated our solution procedure. The calculation sequence can then be followed from the step in which we know our input. First of all, calculate W12A from the isentropic efficiency definition of process 1-2. The isentropic efficiency of compressor is the ratio between the isentropic work and the actual work. We know the efficiency values of the isentropic compression work, or W12S, from previous examples. We can calculate W12A, which would be 247.69 kJ per kilogram. Similarly, we can calculate the actual turbine work, or W34A, from the isentropic efficiency of turbine, which is the ratio between the actual work and the isentropic work. And we get W34A at 376.12 kJ per kilogram. After having determined W12A and W34A, we can apply mass and energy balances in process 1-2A and 3-4A to determine the actual compressor exit and the actual turbine exit temperatures, or T2A and T4A respectively. Combining mass and energy balance equations, we have W12A equal to Cp multiplied by T2A minus T1. We get T2A at 541.88 Kelvin. When compared to the isentropic compressor exit temperature, or T2S, The actual compressor exit temperature is higher due to irreversibility during compression. We also get T4A at 725.75 Kelvin from mass and energy balances in process 34A. Likewise, the actual turbine exit temperature is higher than the isentropic turbine exit temperature due to irreversibility during expansion. Next, the actual heat input or Q23A can be determined from the mass and energy balances in process 2A3. We get Q2A3 at 560.92 kJ per kilogram. We can now calculate the thermal efficiency of the actual gas turbine cycle by using the same definition of what we get divided by what we give. We get the thermal efficiency of the actual gas turbine cycle at 22.9%, which is lower than that of the ideal Brayton cycle that we get from the previous example at 40%. Finally, the back work ratio is calculated from W in divided by W out. In this case, the back work ratio is 65.8%, which is higher than that of the ideal Brayton cycle at 44.8% from the previous example. It means that more work from the turbine is spent in the compressor in the actual gas turbine cycle. The actual gas turbine cycle is therefore less efficient than the ideal Brayton working under the same temperature range. And that's all for this example. Thank you for watching. See you in the next part of this series. Goodbye.